share my screen. So we will be using Octave, and I have already uploaded the guidelines for this exercise. We can check what is inside. So here you can see the main purpose of the work we are doing and the expectations, what you should include on your report, such as this objective, which is defined here, the program code, the plots we will be drawing, and the conclusion about these plots and the results we have obtained. So basically, this is what you need to make in your report. There are no individual parameters in this work, since it's considered to be a brief introduction. I don't know what programming language you were using before, and if you don't have any MATLAB knowledge, so we will take it gradually with simple exercises, but you can believe me, it will become more difficult over the time. So I hope you will be able to keep up, but if you don't, you can freely ask for help, and I will try my best to help you. So what tasks we will be solving? So basically, we will generate a binary signal consisting of ones and zeros. Then we will perform some kind of modulation, although it's quite simple modulation, but nevertheless it can be considered to be a modulation, converting those digits in the memory of computer to a signal representation, which will be also in the memory of computer, but nevertheless will look like as if it is analog signal. And each one digit would have an pulse of rectangular form pulse of 1 volt amplitude, and each zero would accordingly have an amplitude of 0 volts. Then we will add white Gaussian noise with signal to noise ratio of 20 decibel and display this result. Afterwards, we try to receive that signal by detecting it with a specified threshold and see if we have done it successfully. So if we succeed, the plot of the task 4 should be the same as the plot of task 2. So, of course, we may not succeed, especially if we change the signal to noise ratio, and this is objective result. Yes, we couldn't have succeed if there is too much noise, but we'll see how it goes. So we compare the results and then reduce the signal to noise value to 10 decibel. So roughly speaking, if we are speaking about powers, 20 decibel would mean that our signal is 100 times stronger than noise, whereas 10 decibel would mean that our signal is only 10 times stronger than noise. And we repeat those steps to see how it works for 10 decibel. Afterwards, we try another modulation type, convert to bipolar pulses. So for one, we would have, for example, minus 1 volt, and for 0, we would have plus 1 volt. And for 10 decibel signal to noise ratio, we will see how it goes for this modulation. So we will see most probably in the 6th paragraph that it didn't work out for 10 decibel for the first modulation type, and for the second modulation type, maybe it will work. We will that see. So here are additional guidelines and mostly pieces of the code we will need to make our program. Generally speaking, you should be able to complete all this by this code, and examples of what plots are to be expected. So let's do this together now. I will also start a new file. You can of course, write your program in this command line. For example, you can define the signal as a random sequence of binary digits, at least 10, I think it was asked there, 1, 2, 3. And maybe what this way. And you will need to input each command and confirm it by enter, but also you can write a script and launch it, and it will perform all the operations with one click of this button. Yes, so basically, first thing, we will make sure our environment is clean. So we clear all the variables and we clear the console. So if I execute this command, you can see that command line window is now empty once again. That's not mandatory to do, but maybe it's a good habit, I don't know. I'm usually doing that. And of course, I'd advise insert. Of course, you may be not wanting this clear variable when you are launching another scripts, which depends on the results of other script. Then you should be, of course, cautious. But in our works, we will not make such difficult scripts, so you can safely clear variable at the beginning of each program. So our first task is input this data. So basically, we are creating a vector in the memory of computer. I can even say that it's task 1. We add comments by this percentage sign, task 1, and display digital signal. First, we need to define this signal. Unlike C++ or other low-level programming languages, you do not need to define the data type for the signal you are using. It's much like Python. You can right away use your variable and define it on the go. So I'm defining a vector row, so all the elements will be placed horizontally. It is possible also to define a column vector. In this case, you would need to use a semicolon instead of comma. So now I have 7, 8, 9, and 10 binary symbols. That is my digital signal, which we will be sending and adding noise to and trying to receive. And of course, it's a very simple program, but it's very basics, and we will use the similar approach for much more difficult programs, when we will also include coding for error corrections and see how it improves situation. That is basically the last task of your study project, which will be given to you soon. I think maybe next week I will be able to provide you information on this, but currently you have no material to make that study work. So next step is to draw a plot. In MATLAB, there are many types of plots, such as, for example, I can use stairs, which would draw rectangular pulses between those signal points. I can use stem, which would draw the samples themselves. I can use plot, which would draw lines between those points. And the most suitable one for the digital or discrete signal is stem signal, because it draws those samples as stems. Yes. Currently, it's not of a big importance what time is used here, so we can actually draw plots with two variables, two vectors, one defining x-axis and the second defining y-axis. But if we don't specify x-axis, variable, it's assumed to be numbers from 1 to the length of this vector. So basically, if we perform this script, we can see our signal. Usually I am making some visual improvements to the plot. They are not described in these guidelines, but you can easily find information on this in internet. Yes, first of all, I'm turning on the grid of the plot. Then I'm labeling the axis. For example, X label in our case is number of sample number. And Y-axis is labeled with sample value. Now we will have this plot somewhat smoother, and also, well, maybe we will add a little bit bigger Y-axis limits by Y-limit command between -0.1 up to 1.1. So the lowest limit, the upper limit. And this way our plot will not be ending by those values of the signal, because it's easier to see that it's actually 1 if there is a blank space above it. Same way as for 0. So basically, this is the task 1 complete. We have created a digital signal, which we are now going to use for modulation. Now we will be drawing multiple plots. So if we want to see them all without redrawing. So basically, if I now draw a new plot after this code, it will erase my results. And if we don't want that to happen, we can specify that it's figure 1. Afterwards, the next plot will be figure 2, figure 4, and 3, 4, and so on. So basically, I will put that, and this way I will be able to have all my plots and the screen at the same time, which may be useful for you to make those screenshots for report. So the next task is conversion of the digital signal into unipolar pulses, which represent or would represent the analog signal. So basically we are working in a computer, so any kind of a signal in this program is still a digital signal. But if we are visualizing it as a plot, it may look like it is analog signal. So task 2 is basically modulating unipolar, which means a single polarity, pulses. To be more specific. So this can be achieved in many ways, but basically what we need to do is to repeat this sample value. Sorry, that's too big. To repeat this sample value so often that it would merge into a single line. So for example, I'm putting that sample repeating here, yes. And the more often we repeat it, the more closer those points are to each other, and the line is drawn as if it is an analog signal. So basically we need to repeat each of these symbols multiple times. Now, of course, we can do that manually. Let's name this signal as TX, X transmitter. Yes. And let's just say I will now repeat each signal 3 times. And we'll separate it. But as you can imagine, 3 times won't be sufficient, and we'll need to do much more. Well, maybe it's enough. Then we will plot this signal. and see in figure 2, so that we don't lose our information. Now, I'm using here those commands on the same line, but of course you can also use them in separate lines. It doesn't really matter here in this language. Neither does this semicolon at the end. It just means that we do not want to see a result of execution. For example, you can see that here for S I am putting that semicolon at the end, and here I don't. So I will see in this console after I execute the script what is actually inside of this array. Yes. So if I want to suppress that output, and then I put a semicolon, and it won't output that information anymore. So as I was fearing, it's far away from rectangular pairs. We need to repeat much more often that signal. Let's say, for example, 100 times. Of course, we will not be doing that manually. Well, there is a function in MATLAB, and you can actually get help on any function you know name of, for example, help once, which tells you how you can create a matrix consisting of ones. For example, if I put ones 10, this would yield a 10 by 10 matrix consisting of 1 elements. Now I want to create a row of ones. This way, the first index is the number of rows, and the second index is the number of columns. I need to specify, let's say, 100 columns, and I'm able to merge different arrays, different vectors into a single vector by this operation. It's the same way as I was specifying the initial vector, yes. So basically it's, I don't remember that name. It was a mathematical term, but I will remember then and tell. But right now it means that we have one vector consisting of one element, one vector consisting of one, and we are merging them all together into a single vector. So here I am creating a vector consisting of ones, 100 ones. Then I'm having a 0, so vector consisting of zeros. And well, this is much more tolerable and possible to do by hand, rather than writing those actual 100 ones or zeros. But still is not good enough because I need a lot of handwork. Yes, so you can see that it is now actually a rectangular form pulse, but it's still not convenient to do so. So there is another command called kronecker multiplication, which I'm going to use for this case. So basically, what does kronecker multiplication if we have some vector A or even matrix? So it's not only an effect for vectors, it's for a matrix A11 and up to A22, and matrix B then calculating of kronecker multiplication between those two matrices would take this matrix B and put it instead of each A matrix element and multiply it with this element. So in this position, there would be A11 times entire matrix. Here would be A21 entire this matrix, A12 entire this matrix, and A22 entire this matrix. So this is exactly what we want. We want to substitute this one with entire row of ones. So we are going to use kronecker multiplication to solve this task the most simple and straightforward way. So we are going to put our elements into S, and the second, our B matrix, which will be used to replace each element would be ones. 100. So basically, if we multiply 101 symbols by 0, we get 100 zeros. If we multiply it by 1, we will get 100 ones. Let's see how it looks. So once again, I'm going to simply copy this formatting to improve visual style of the plot. Here we will have time in certain units, which are irrelevant right now. And here we would have a signal. So this way we have two plots, and you can see that this digital signal has been somewhat converted to analog signal, which we will add noise to. So the next step is adding noise to this signal. Let's do that now as task 3, adding AWGN to a modulated signal. So it's a modulated signal, the signal that's a result of a modulation. It's not information signal anymore. So here we also have some guidelines on how to do that. And basically what I was explaining here to you is not written here, but that's additional information, something to think of for you. So before we use this AWGN function, which is also built-in MATLAB function, we can move it here and read. So, one more moment. If you are using Octave, then you need to load specific packages the function are belonging to. So you will know if which package to load, because it will tell you. See, I am trying to access here AWGN function, which is a function from communications package. So it tells me that package is not loaded yet. You need to do this only one time after you have launched Octave. And if you will close Octave and launch it again, you will have to do it again. But basically, you do not need to do it each time you are calling AWGN function. So now we will be able to read this information. You do not need to do anything of this in MATLAB, because those toolboxes are dynamically loaded and unloaded when needed. But in Octave, in order to keep memory clean, those packages are not loaded by default. So basically, there are additional options, of course. We can specify the power of our signal, but all we need to do is specify our source signal, initial signal, which is needed to be noised, and the signal to noise ratio. Then it will automatically calculate the signal energy or power and noise power, and will add it accordingly. So it will calculate signal energy from X. It will calculate the noise power given this relationship. Yes, if we know the ratio and signal power, we can find noise power. Then noise power yields us variance, which can be used to generate random process with Gaussian distribution, and this process is added to our signal. That's how this function works. We will use it. But before we are going to use it, we need to specify signal to noise ratio. We will specify it initially as 20 decibel, as is asked per our exercise conditions on task. Yes. So this is signal to noise ratio. And then we can create a received signal. This would be signal at the input of a receiver. We are not adding here propagation attenuation. Yes, so we basically have a, let's say, ideal channel. which does not reduce the amplitude of our signal, but adds a noise nonetheless. You can consider that we are transmitting on a very short distance, and the signal just cannot be attenuated over such a short distance, or maybe some optical fiber or high quality cable. Anyway, there can be some assumption made to justify this choice, but the reason of this is to make this program simpler. We do not need right now that complexity. So we create a received signal as Rx as noisy version of our transmitted signal with specified signal to noise ratio. This way we add noises. So the remaining part is to draw a plot, which once again I will just copy and paste from already prepared fragment of the code, just making sure I am making a new window for this plot and actually drawing the correct signal, which is received signal, and let's see how it looks. So here our Y-limb is actually truncating the results, so we may be wanting to get rid of it. Yes, in this particular case, because actually due to noise our value can be more than 1.1. This is caused by a noise, and lower than minus 0.1. So now we will design a receiver, and for this receiver, for this detector, we must specify the threshold of 0.5, which is the average value of our signal, and well, anything that is above this average value should be interpreted as 1. Anything below should be interpreted as 0. Basically, this way we are going to achieve our result. Of course, this is not how actually receivers work, optimal receivers at least, which we will be studying, but this is a nice introduction and entire concept of the idea. We will make it much more difficult over time for radio signals as well, but at the present moment, it's just that as simple. I will show you how to add this threshold here in this plot as an additional line. So if I'm having some plot drawn already, I can always add extra lines to this plot by performing function hold on, drawing a new plot, and accordingly hold off afterwards, so that we don't draw any extra stuff that we don't need on mistake. Maybe we forgot to change this figure and it will draw on top. But now, how do we draw the line? From the course of geometry in school, you know that in order to draw a line, we need just 2 points, here and here, and then plot command will connect these 2 points with a straight line. So we need to specify coordinates of the first point and the second point. First is X coordinate, and then is Y coordinate. For the starting point, the X coordinate is 0 and ending coordinate is 1000. We can, of course, make it more universal and put here not 1000, but a length of our signal. This way, if, for example, some of you have specified on error here 9 symbols or 11 symbols, it will work for you as well. So basically, it's advisable to make this not hard-coded. It's such a term when you use number, then you change something here, and you are forced to look through your entire code and make corrections everywhere. So it's basically organized this way that you only have to change something in the program and everything else is being recalculated accordingly. And yes, something. Activity. Scilab. I think it should be possible. Maybe you just will need a little bit different syntax on these commands, but I think Scilab is also very similar to MATLAB and should work. You can even probably work on this in Python, especially considering there are some modules that make it possible to write in almost MATLAB style. So, okay, let's return to this. So we have specified x coordinate for our straight line. Now we need y coordinate, which is the half of this amplitude. Yes, so this is, in our case, 0.05. Once again, we could actually make this calculate this parameter rather than change it manually, and actually it would be a good idea to do so because next time our threshold will be different. So let's just calculate this threshold. So we can calculate this by finding the difference between minimum and maximum values. So we take maximum possible signal value and subtract minimum possible value of our signal. That would be entire difference, and we need to divide it by 2. So basically we are finding an average signal value, and this way we will be able to use this threshold also for a detection further. So this way, after we go to the step 5, converting to an RZ code, we will not have to redefine and change manually that threshold. It will be calculated automatically. The only thing is that actually we need to put here STX rather than S, which is transmitted signal. Well, that's basically only because I am seeing a few steps ahead and knowing how we will solve our next task. And nothing was wrong with S, but it will not work as we desire in future. So knowing that fact, I am already correcting that here. We can take that, calculate threshold automatically. Avoid necessity to change it manually later on. So now I'm plotting this. Here is a vector of x coordinates, here is a vector of y coordinates, and we should see an extra line here, which is this threshold. And our next task is very simple. We must compare signal values at each moment. Once again, we can do that in many styles and ways. Task 4, detecting signal. Basically, you could write force loop, and for some k from 1 to length of SRX, for example. This probably will work, but it's not how we will do it. Then you can create if comparison, if SRX index at k is more than threshold, then S detected should be index at k, yes, should be 1. Otherwise, as detected, k should be 0. And that would be very like in C++ and something else. But in MATLAB, actually, we can perform this operation over a vector. For example, let's take a vector A as a column in this case, consisting of these numbers, and we want to know which of them are greater or equal than 3. So basically, I'm just saying greater or equal than 3, and it will output me the result. It will output the logical result, but this logical result is exactly what we want. So we won't have to convert it somehow or do something about it. It is exactly what we desire, and it's fine. So we will use this relational operator instead of this entire loop. This way, as detected is as received greater than threshold. And that's it. So in MATLAB, you can vector perform operations, unlike in C++, and that's a great convenience. So the remaining thing we need to do is drawing a figure for this detected signal. Also, it will be regular unnoisy signal, so I'm putting back this limit, and let's see how it looks. So this is figure 1, figure 2, and no figure 4. Figure 4, no, because I have named this variable as thresh, not threshold. So that's a mistake. And here we have figure 4. As you can see, if we compare figure 4 and figure 2, they are exactly the same signal. So in this case, we were able to correctly receive our signal, even despite the noise. The noise, however, was not that strong, as you have already been told. This means that our signal is 100 times stronger than noise. So in this case, if we change this signal to noise ratio to 10 decibel, which means signal is 10 times stronger than signal, we will have some problems, because in some positions, as you can see, the noise leads to a signal degradation below this threshold for 1 and above for 0. So if we use it this way, we will have such, well, not so entirely clear picture, but we can see here that mostly this is 1. So yes, this is not a good detector. We will use much better when we will calculate the energy of this signal, entire energy average value, and compare this average value. So basically, we could have calculated average value over this interval and compare it with 0. And that would be much better result. We will not do it today, however, maybe next time. But we can see that for 10 decibel, our proposed detector is unable to work correctly. Now let's modify our signal as is described in last guideline. We can create so-called NRZ signal, non-return to zero, which is a bipolar signal, meaning it will have -1 volt and +1 volt values rather than 1 and 0. And effectively, this will give us twice greater magnitude. And well, in this case, our signal should be able to deal with noise much better. We'll see how better it will be in our case. So the only thing we need to do to make this NRZ code is adding this mathematical expression right before adding noise. So what is that mathematical expression, how it works? Basically, we need to convert our 1 value to -1 and 0 to +1. Actually, we can create a system of linear equations. So basically, this is our given result and this is our expected result. So this is x and this is y. And we are using here two unknown parameters, which can allow us to calculate y from x. So basically, we will have two equations of the form ax plus b, where we need to find what are a and b. We can write two versions of this equation by using this given data. So basically, we have -1 equal to a times 1 plus b, and we have +1 equal to 0 times a, which leaves nothing, plus b. So we already know that our b is +1, and here, putting it here, we can find our a, which would be -2. So this equation is, in this case, written down as follows: -2 times x plus 1, which is exactly the same except for x is as transmitted and y is the very same as transmitted. So we write over this variable with the new values. So this is how it's done in our case, purely mathematically. So we do this before adding a noise here. Somewhere, well, maybe just as well as here. AWG, -2 times STX plus 1. And afterwards, we add noise. And let's see how it works. It won't work well because our threshold is wait a minute, our threshold is 1, which is incorrect. STX maximum would be 1. Minimum would be 2, but we need to have it in between. Wait, then that means that this equation is incorrect. Let's see. It should have been 0 for this case here, for the average value, because our signal is unipolar or bipolar. You can see here is -1, here is +1, which would lead to average value of 0. And -1, which also wouldn't be correct. So most probably this means that we did something wrong here. Yes, of course, it should have been plus. For 0, it really didn't matter. When minimum was 0, plus or minus, we didn't have error there. And now, if we add -1 to +1, we would get 0. 0 divided by 2 would give us 0 threshold. So this way. And as we can see, it didn't really work out well. even though those pulses look rectangular, we have received the opposite signal. So if we had 1 here, we have 0 here. If we had 0 here, we have received 1 here, which is inverted signal. This is because our logical function here compares and returns 1 if we are above threshold. However, if we see here, figure 2, then 1 should be received when we are actually below threshold. So we need to change that operator to opposite, to less than. And then it would work fine. Yes. So now these pictures do match. And unlike the first modulation type, in this case we have not been affected by that noise, and we can try another signal to noise ratio, for example 8. In this case you can see some problems begin to occur. However, there is not so often that signal noise led to exceed this threshold where it shouldn't have. Well, that is a random process. Because of that, we need some averaging procedure to account for this random process. Any type of averaging smooths out that randomness. Any constant component after averaging remains the same. Any spikes and very rare events are averaged down to 0. So basically the solution would be perform the averaging of this signal before actually trying to compare it to threshold. We will speak of this most probably next time. So for today, that is all I wanted to show you. I hope you can reproduce these results and create your first report. As for the terms on reports, you can make that during all the semester. There is no strict date when you should send this report. You just need to do as much of those reports and course project and exam to earn as high mark as you can. Yes, so basically your mark will be decided based on what reports you have submitted by the end of the course and how far you have been able to calculate your study project and exam tasks. So there is no hurry in this, but also I wouldn't recommend putting that into the queue or forgetting about it. It's better to complete it at once and be free of the responsibility. So thank you for your attention, and I hope you liked this information and exercise, and we'll see you next week. If you have any questions, please don't hesitate to write me. So thank you for attention and goodbye.